Yeah, thanks everyone for coming. I'm Micah Hausler. I'm a principal engineer at AWS.
And I'm Lucas, working at Upbound as a staff engineer, and we're both in the Kubernetes community in different ways.
Yeah.
And today we'll talk about some ideas to how we could secure even more of the things.
So to start out, we just kind of wanted to ask the question, like, why does end-to-end security or end-to-end authenticity specifically matter? Well, actually, first, no, we jumped ahead. Outline. Okay, so we'll talk about an overview. So we've got to talk today just about end-to-end authenticity. Why does that matter? So we'll talk about why that matters, kind of common attacks, and why you might actually care about this. And then the good news, like, okay, how do we mitigate this? And so we'll talk about some of the methods that can be used to mitigate these kinds of attacks. The kind of step-by-step of what does that take. And we'll actually have a demo too and kind of talk about next steps, like what's the future in this space.
Yeah, and well, here's a demo link. So actually the demo involves you. So at the end of the talk, you can pull up your laptop and actually try it out yourself. We have a server running for this.
Yeah, so kind of beginning here, why does this matter? So typically in a cloud-native system, you'll have microservices, right? You'll have some services talking to other services. And typically, you might secure this with mutual TLS. So you have TLS on the server, but you also might have client authenticating itself using TLS, like an X509 certificate. But you also might be using a bearer token. So in this case, you might have a user whose name is Lucas calling your service with a bearer token. And then you have some gateway that is calling some backend service, and it's doing its own MTLS with some backend service, right? So as a user, you're not even aware of this necessarily. It's just downstream of you. Between the user and the server, you get authenticity, knowing that, okay, I'm seeing that the certificate is by this server, and I have this ID token, and it's authenticated with the server, and you get confidentiality. Your data is encrypted in transit. Between the gateway and the backend service, you also get authenticity, right? In the base and best case, there's maybe MTLS. You have server to server talking to each other, so there's trust both ways. The integrity, the message is signed at the transport layer with MTLS. So if a bit flips in the middle, like you have a bad network gear or whatever, like there will be retries and stuff. And at the TCP level, and you know that the content is going to be conveyed correctly. And then finally, confidentiality, because it's TLS, it's encrypted at the network level, so no one can see that content. But what happens if you have a hijacked or misconfigured gateway? Lots of bad things can happen in the middle, right? You can have your authenticity basically can be compromised. You can maybe have the correct token forwarded, but maybe the content of the message changes, right? That's not something that the client necessarily wanted. Very common in these kinds of systems, especially when you're using bearer tokens, you log things lots of times. What happens if you log the authorization header? Now your token that's replayable across requests is logged in the system, and maybe you're not aware of it, and it's just in some log that persists for 10 years because that's what security said that had to be done. And that's not great. So the client doesn't even necessarily know that this is happening. And their request might, again, be mutated in between this hijacked gateway and the backend server. So the server would see multiple tokens, not just the one token, of the correct user, and have access to all of these. And then could replay those on, again, back to the backend server with maybe not the correct user. So in this case, if I'm Lucas and I'm talking to the gateway and I've got token A, the backend could talk to, or the middle gateway could talk to the backend service using a different token, but posting Lucas's data. And similarly, like it could also change the content of the message as well. So not only replaying one user's token for, credential for another, but also, again, modifying the integrity of, violating the integrity of this system. So every component in this request chain has to be fully trusted, and that, in this world, could be problematic. At least the data is encrypted, right? So that is something that you get with MTLS, but you sort of lose all these other important things about, like authenticity and integrity.
And it could just be like misconfigured as well. It doesn't have to be malicious. Maybe you just did a bad change in some configuration somewhere. Short OIDC primer. So what is OIDC? Because we'll look at some extensions of it. So OpenID Connect protocol. If you ever used SSO, then that's what's happening behind the scenes. What is nice about OIDC is that the verifier, which is the server here, doesn't actually have to kind of synchronously call out to the identity provider when it sees a token. So instead, it downloads the public keys that it can use for verification in the very beginning. Then the user, logs in, gets redirected back with a token, thanks to giving the username, password, MFA, whatever. And then when they use that token, the server here can look at the signature of that token and using those public keys, figure out the identity. So this is good because, the application, our server in this case, the relying party, has an easy time validating this token. We can propagate all kinds of extra information about the user, groups, email, all that kind of stuff. Not too much, of course, because it's in a header, but still. And we have the problem, though, that we just talked about, that it's a symmetric credential, so that when you actually put it with the HTTP request, if someone happened to see it on the way, you can forward it, do bad things with it. And also, it's not bound to request content. So these are some things that we would like to mitigate. So how do we do that?
Yeah, so next, this is the good news part. We'll talk about kind of how do you mitigate this problem, because this is kind of, even if you're using MTLS like we discussed, like bad things can still happen. So there's a IETF RFC 9421, you can go check it out, for HTTP message signatures. So this is an open source part of the HTTP spec now to sign requests between a client and a server. So just take this idea. A client can sign a security-sensitive content of the request. So security-sensitive content being, what's the URL? Like, what are the headers in this request? What's the content? Like a header with a SHA-SUM of the content. Within either an asymmetric or a symmetric key. And then the server can validate that signature applies to that request. And it actually matches for the request. So if I have a post to users and I have even if I have a bearer token, and I put a signature on it, that signature is going to be a signature of the request itself. So because of how hash algorithms work, if you change any of the bits that go into that hash, the hash is not going to match anymore, right? So if I change the URL, if I change any of the headers that are signed into this request, if I change any of the body, the signature is no longer going to match.
And the nice thing about it is that, with TLS, everything, you don't get to choose what is important in this request. Everything is encrypted and kind of, if we would have a case where TLS would go all the way through the middle kind of box, the proxy can't make any decisions on specific headers and stuff like that. Now we get that option, but still read-only.
Right. You can obviously like end-to-end encrypt a system. So this is like used in things like Apple's PCC, where they talk about encrypting a request at the iPhone and then propagating that encrypted request all the way down to like the inference server, and that can have like advantages in terms of privacy, where your middle boxes can't even see the request. But as Lucas just said, like if you do want to do microservices or something where you do want to route parts of the request to a different backend, but you still, so you don't necessarily need encryption all the way through end to end, but you want to do validation of your authenticity of your message, you can do that. So what happens is if I have a gateway, and even if I can see this request, right, I can see the headers, I can see the signature, I can pass that on all the way back to my backend service, which can do a verification to say, okay, I know, in this case, I know the key for Lucas, and I can verify that this signature was created by his key. Now, if there's any modification of any of the signed headers or the content in the request, it's going to not authenticate. But I can add additional headers that might not be signed, and that will work fine. So if I'm propagating an HTTP request through multiple services, say I have like an Nginx or something as sort of a proxy layer, I can still add other headers. They just can't be signed headers. So that leads to a key distribution problem, classic, right? Like, how do we distribute keys? So this also worth noting that this RFC is in part like pushed by AWS and Amazon, as well as other people in the IETF. And this is somewhat inspired by AWS's Signature version 4 or SigV4, which uses a similar idea of using a secret key, a symmetric secret key, and an HMAC. So this is basically putting your secret plus the content of the request into a hash, and doing that a couple more times on different parts of the request. So hashing, adding, and coming up with a signature. And so what AWS does is very, very similar to this in all the AWS services, where the client, when you're a client of Amazon, you get your access key ID and your secret key, and maybe a session token if you're an IAM role. And when you use an AWS SDK, what that's doing is doing all this HMACking. So it's saying, okay, I have my client secret. I'm going to add that with parts of the request, hash it, add another part of the request, hash it, and then it generates this signed tokens for that specific request. And that token is only valid for that specific request. So that's just what the AWS client libraries do. And AWS has an internal service, the auth runtime service, or ARS, that does the validation of this. So when you make a request to an AWS service, especially if you're using an IAM role, your session token gets sent to the service, and that's a signed header. That gets passed to ARS by whatever service you're calling. And that token it has your secret in it, except it's encrypted. And so the service you're calling calls ARS, gets the decrypted secret key, and now can basically rebuild the hash that you included in your request and validate that, okay, yes, this really is you. That's the magic of AWS SigV4 kind of on the server side.
But the problem here is that still the client has to distribute, well, you get these magic keys, random bytes from an API call, but you still need to get them somehow to the
right.
client.
It's a pre-shared secret. You got your secret access key from AWS. AWS told you what it was. You didn't get to pick what it was.
Yeah. So on a high level, what are some other alternatives, and especially as the formalization of HTTP message signatures supports both symmetric and symmetric keys. Let's take a look at using asymmetric crypto for this. So the application or the server in our case, it trusts an identity provider, and this is, you choose, it's your configuration. The idea is that the identity provider will attest the client, so like using, username, password, whatever kinds of thing when you log in, maybe MFA. But once that's done, then identity provider has figured out who you are. Now we add one step where the client actually will have a key, and now the identity provider associates the key that they have with their identity. So then from the application perspective, because it's trusting the identity provider, it can also trust the key of the client. So there's a couple of ways to do this. This is the normal OIDC flow that we just talked about in a little bit more detail. Actually, first you get redirected to the identity provider page, and then they redirect you back. You get a code in the redirect, a one-time use only, that you then do a normal HTTP post request to get the signed token. And then you use the token as you like. But if we add one thing, if now the client actually has a private key, it can be ephemeral, generated in the browser or whatever, non-exportable. Now you do the same thing, you redirect, get back, But then when you post the code, you actually sign a nonce, like a challenge from the server, and using your key. And now we see here that like the token that you get back is actually like has this confirmation claim. So like it says that identity provider, check that you actually do have this private key on your, well, in your browser or in your private memory somewhere, which means that now you can use this when actually doing the HTTP message signatures request. Because then the server will, the application will look at, well, is a token valid? Yes. It will validate it using the, well, orange is here for the identity provider key, green is for the user's key itself. So we'll validate using the orange key, see that, well, this is a known user. Oh, this user has this key. Let me see if that actually checks out with the signature for this specific request. The problem with this is that actually you need to have some support for this protocol. It's also another IETF RFC 9449, but it requires changes support in the OIDC provider itself. So there were some smart people at OpenPubKey that figured that actually we can use a nonce for this, because the client, when you start the login flow, actually get to choose a nonce. So like a value that should only be used once. You add some specific meaning to it and derive the nonce, well, from a random value, but still from a key as well. So now when the application is validating, it can, well, do the same thing. It can recreate the nonce from the data that it has and then see that does it check out or not, i.e. does the user actually have this key or not. So that's a link between the user-provided key and the trust of the identity provider. And well, now we don't need to this work with any OIDC provider because it's by the spec. So this is great. But then, just for fun, GitHub is also a public key database. If you add an authentication token, SSH authentication token, actually it's going to expose your keys here publicly, right? So we thought it would be fun to do a demo with this and actually use, well, GitHub as a key database. And now, like, because both the client trusts GitHub and the server we configure to trust GitHub, actually we can sign some messages and have some fun with this. So yeah, how's the demo going to work?
So yeah, so what we'll do here is basically, if you've already scanned the QR code, oh, it doesn't work? Okay, well, sorry. So we'll have, we have I'll demo it here in a second, but we have a client that, so you log into GitHub and you register your public key with GitHub, and then as a client you can make a request signed with that public key to our demo server. So it's encrypted with TLS. You get like transportation level security and encryption, but then you also will say, okay, here's my, just say to the server, here's my GitHub username, and then generate a signature including that GitHub username signed. The server will then, well, actually, you'll do it through an Amazon load balancer is the implementation here, which passes it on to our backend server. And that server will look up the keys for this username and then download those and make sure that the key ID specified in the request is one of the keys in GitHub and is actually properly signed. So if you wanted to participate in this, you can generate a new key if you don't want to use one of your existing keys. If you don't trust us to run this client with and passing it your GitHub private keys. We promise we're not hacking your GitHub. But you can run this regex demo. And I'll do it here in a second. But you'll basically pass it the key to say, here's the key I want to sign the request. Here's my username. And what it will do is actually just spit out a curl command for you to run yourself. So you can see that we're not doing magic, a lot of magic behind the scenes. You can inspect the source code. This is all open source. And then actually execute that curl command. So let's do that really quick. Thanks. So I've got my server here and my client. And what I'm going to do is, let's do. So I've got my go mod. I'm going to go run main, and it failed to work because I didn't give it a file, and we'll see the arguments I have. So I'm going to pass it a key, and that's just going to be SSH, IAD, ECDSA, and then dash username, my GitHub username, and run that. And so this spat out a curl command. So this curl command says, okay, I'm going to make a post to regex.dev.micahhausler.com/hello. Here's my content type. Here's the signature input. So this is part of the RFC is to specify, okay, tell the server what goes into rebuilding this signature. And that includes things like the method here that I'm specifying, the target URI, so the whole URL, the content type, and this X GitHub username. So if I change any parts of those requests, the signature will change. If I add new headers that are not part of this signature, that's fine. The request still goes through, and the signature doesn't change because those aren't those aren't what goes into the signature. And then I also specify here's the key ID. So it's just a SHA-512 of my public key. And then I have another header for the signature, which actually has that's generated signature, and I throw in my GitHub token. So let's try this. So if I do that, I get back, hello, Mike Hausler. So that worked great, right? Okay, like.
So it's authenticated, it works.
It's authenticated, it works. But what happens if I go ahead and I change the content type instead of to JSON to YAML with the same credential, right? I'm going to get unauthorized. That's because the server, once it saw my request, is like, oh no, you know what? That signature didn't compute. That's not signed by that key, or that key did not. The signature does not match the bytes put in that were signed by this key.
So this could, for example, represent the case of the ALB being misconfigured or something to set some
Right.
specific headers that shouldn't be set.
So I've got some pods running in this cluster behind a ingress load balancer. And if I want to get the logs out of this, you can see that, okay, I authenticated successfully as Micah Hausler, but then I had a second request.
It was even, yeah.
Yeah, that wasn't even valid. So if any of you log into this, I'll see, hey, thanks for trying the demo. But that would work with anyone else's GitHub username because it's just taking the signature and validating it against your GitHub keys.
Cool. So what's next? Well, there's a lot of cloud native folks here, so I'll talk about how to integrate some of these into Spiffy. So, well, now we had, for kind of simplicity, gave some examples on, well, SSO, like human clients logging into something using their human identities to access systems. But what is going to be as important, if not even more, is going to be, well, if we have these long chains of like a request hits a gateway, and then we have like 5 services in between before it hits a database. Now, like verifying that actually that request stays same across the whole request path is going to be pretty critical. And this means that like workload to workload authentication and request authenticity is good to have. So Spiffy is well, standard for distributing identities to workloads. The idea is that it's the kind of the bottom turtle of all of this, kind of giving the identities to the workload. So when a workload starts up, it's going to ask like, who am I? What are my identities? Through a gRPC API, which is well known. Then it's going to, well, attest. So then the agent running on that node is going to figure out that, well, who is this workload? What is this workload doing? What identities does it map to? And when it figured that out, it's going to, well, sign and give a, well, X509 cert or a JWT token to the workload, which the workload then can use in different ways to authenticate. But then, so that's normal Spiffy. Now there's another IETF internet draft, so third one of this presentation called WIMSI, so Workload Identity for Multi-System Environments going on. And it's, well, idea there is to kind of add to Spiffy a new type of token. They call it a WIT, Workload Identity Token. The idea is exactly the same as DPOP and OpenPub key, in that a workload gets a private key. At the moment, it looks like Spiffy is going to generate the private key and give it to the workload. So Spiffy can kind of control the signing algorithm and stuff like that. But then the workload gets a public key, so a private key. The issuer, so Spiffy, binds the workload identity to the public key in the token that it gives. And then finally, anyone else that is kind of, well, wanting to authenticate this workload is then able to, by trusting Spiffy, look at the token is valid itself. And then when they know the token is valid, then they just get the key there encoded in the token and can then, well, authenticate this HMAC or HTTP message signatures thing as well. So that's it. And yeah, thanks to Evan and Peter from Spiral for answering questions and just making sure this was correct with the current thinking. There's a Spiffy pull request that you can check out for more information about what is going on here, and maybe by the next reject we'll have something more concrete. We'll see. Yeah, that's it. Thank you very much.